As they're setting up, our next presenters are Noah, Isidore, and Jesse, and talking about the Everest Project. This one should be unmuted because it's got cruise. Right. So you should mute yours and we can just share your screen.
You want to unpin me? Oh, never mind.
Right, perfect. So, good morning, everyone. My name is Noah. I'm Isidore Simon. I'm Jesse Cook, and we are behind the development team of the Everest Project. So the Everest Project consists of a portable weather station that's going to be able to examine severe weather conditions for a long term, particularly 3 months, and study the climate change conditions that would happen at this particular time. So our inspiration and mostly our interest to develop this project was due to our knowledge with already some of the stratospheric ballooning projects that we've already done over the summer and over the course of some of the years. But additionally, we wanted to study the severe and long-term weather events that would happen at these particular high regions, like mostly higher than 7,000 meters or like around 23,000 feet. We also want to collaborate with the climate capture mission made by the Interdisciplinary Climate Change Expedition led by Jackie Clancher, which is to gather Earth's most critical environmental and climate data. And this sounds good and all, but overall, what's the meaning for spacecraft? Since we're going to be testing these on like severe weather conditions, this will mean more robust systems for our high altitude ballooning expeditions. And also we would be able to get much better data gathering, data collection for these particular missions. And speaking of sensors, I'm gonna give it to Isidore.
All right, so looking at some of the sensors that are on board the inside of this casing here, not technically a sensor, but still important, is the brains or the computer behind this operation, which is the TNT 3.5 microcontroller. It's selected in part because it is 5-volt tolerant. With other renditions of the TNT microcontroller, you'll see that anything over 3.3 volts will sometimes kill the system. But the TNT 3.5 has proven that it is, if it does get accidentally more than those 3.3 volts, it still will survive. It is programmable with Arduino and has an average current draw of about 45 milliamps, which is pretty standard for a microcontroller. Something that we investigated and we're still continuing to investigate with this project is the ability for the TNT to hibernate. So possibly having like an Arduino Nano constantly on and being powered, and then only supplying power to the TNT 3.5 when we want to collect data. With the TNT 3.5, the micro SD card reader is already installed, and it will save data in a CSV style or format. And they're quite small, so even over those 3 months periods where this may be out in the wilderness, it still will be able to store that data for that extended period of time. Next up, and another not technically a sensor, but still important, is the OLED screen, which is what we're currently using to display data. It's monochrome blue on black and has 64 by 48 pixels. In its current configuration, when it's displaying data, it has a draw of about 10 milliamps. But if every pixel is on, it does draw about 20 milliamps. And it's capable of running from -40 to positive 85 degrees Celsius. So we'll be more than able to survive the conditions on Everest. And again, this allows us to measure any of the data that the system is recording. But most importantly, it's able to monitor the battery through some things that Noe will talk about in a bit. But over those extended periods, it's important to know the battery life and then be able to recharge it if necessary. Then actually getting into the sensors, we have the U-Blox M8N GPS. It's accurate within about 2 meters. However, this can fluctuate quite a bit, especially with altitude. But because we'll have good latitude and longitude readings, we can place that over a map and then just get altitude readings that way when it's out in the wilderness. It has a maximum altitude of 50,000 meters, but the height of Everest is only about 8,000 meters, almost 9,000 meters rather. And so it won't necessarily be a problem for this project. When you power up a GPS, it does have to restart and relock with that satellite constellation. And so from a cold start or having no power, it can take up to 26 seconds to get that lock. But if we do supply power to it continuously, it can get a new lock about every second. And again, it still operates in that large temperature range. Additionally, we have two thermistors in the project on the board. One is mounted internally and it can measure the temperature of the board for its health, but also can be moved to monitor the temperature of the battery if that's what's desired. And then finally, we have another one that's mounted externally, and they're able to measure temperatures from -80 to 150 degrees Celsius. And they're accurate within plus or minus 0.1 degrees Celsius. A lot of our sensors do have temperature readings on them, but this is our most accurate one by far. We also have the m07 pressure sensor, which also measures temperature. It ranges from 1200 down to 10 millibar, but to put that in like elevations, it's from below sea level to over 100,000 feet, and it's accurate within plus or minus 2.5 millibar. Again, it still operates in that large temperature range. Another sensor we have here is the SHT30 humidity sensor, and it measures humidity and relative humidity from 0 to 100%. And again, it's in that large temperature range. It is covered in a wire mesh coating, which prevents actual water droplets from getting into the sensor, but it still does allow that humid air to pass through so you can get an accurate reading. Something that we didn't initially realize with the sensor, but we realized after testing it out, is there is a heater located inside. And so in a bit, we'll show some data from a flight that we just recently had with this project. But you'll see fluctuations, and that's due to the heater. The heater actually removes humidity from the encasing, so you're able to get more accurate readings. And then that's all I have for sensors.
Yeah, perfect. So now I'm going to be talking about a little bit about power. So in order to power the TNC and to guarantee a long-term consistent log of about 3 months, different powering technologies, sensors, and components were actually used to measure the power efficiency of the system, as well as to effectively power Everest without need of some kind of excessive overload. So first of all, we're going to be taking a look at some of the powering and charging technologies over here, and both passive and active. So the first one is going to be a 2-watt 6-volt solar panel. This one is going to be our method of passive powering technologies. So this one has a medium-sized dimensions such as 5.4 to 4.4 inches. It has a nominal voltage of 6.5 volts at around sea level, but at higher altitudes, all the way up to 100,000 feet, it can reach like a peak voltage of 8.5 volts. So even then, like you can have like greater loads for this particular solar panel. You have a max current rate of 330 milliamps, and it has a cell efficiency of nearly 20%, actually 19%. We also have a crank powered or dynamo charger. That's going to be our method of active charging. So with that, we're just going to be obviously spinning the rudder over there and converting that kinetic energy into electricity. And it's going to be parallel, connected in parallel with the solar panel wiring. And this will provide like any kind of emergency power generation in case the solar panel falters. In terms of backup power, we looked at high capacity lithium ion polymer batteries. We looked all the way up to 10 amp hour batteries. So those ones would be within the range of 3.7 volts. And these were actually encouraged so that we can have long-term missions, particularly for Everest. So you can expect with these high capacity batteries to have like about 95 hours of charge of battery within a full charge. And that would be with no external charging, not considering like dynamo or not considering the solar panel as an external power source. In terms of load output, we have a DC solar LiPo charger. So this one was used in former spacecraft missions. So with this one, we are connecting a battery and a load connection, and we can charge the system all the way up to 1.5 amps with just the DC and solar panel plug. And it's always regulated to 4.4 volts. So in other words, it's perfect so that we can have like 3.3 volt regulators or 5 volt power boosters, which is what we have over here. So we have a power booster that's going to go all the way up to 5 volts, which is going to be good for 5-volt tolerance sensor, such as the TDC 3.5, and it has a 96% operating efficiency. And with that, you can get like very small voltage reductions. But aside from that, it works pretty well. In terms of monitoring the power and the battery, we have a fuel gauge that's actually going to be measuring the voltage and the change in percentage. So it's going to be running with these kinds of batteries, and it'll be helpful to determine like the change rate at which the battery like loses its charge. And we're also going to be including a current sensor over there as well. So this one provides readings of the consumption of the battery, and it'll help us estimate the consumption of it during a continuous amount of time. Next, we're going to be talking about structures, which Jesse comes forward.
Thanks, Noe. So this is the first time that the Minnesota Space Grant is building a payload specifically for this purpose. Surviving a trip to the stratosphere, 3 hours, albeit rough and tumble a little bit, that's one thing, but this has to survive for potentially months while being carried along on one of the most dangerous journeys a human can attempt. So that's why in our initial decision regarding whether we should design a purpose-built case or purchase one from a trusted manufacturer, we opted for the latter. We're definitely considering building our own case for future iterations of this project, likely to be implemented next year. But for this year and for the deadline we're trying to meet for April, we're going to go with a Pelican case. Initially, we were considering the Pelican 1020 because it has a more or less square shape, at least compared to the other micro models. And we thought this would be best for space efficiency, considering that the board itself is approximately square, but there's still the issue of where to place the peripherals, namely the battery, the external displays, which I'll elaborate on shortly, and the solar panel. Does it go inside of the case, taking in sunlight through the transparent lid, or do we put it outside, allowing it to risk damage? Ultimately, we decided that the Pelican 1060 better suited our needs owing to the extra internal space and the added surface area on the lid. So even before we selected this case, we knew exactly which solar panel model we were going to use, the same one that Noe just described. And as it happens, it fits like a hand in a glove with the selected case, and that's more or less by happy accident. Like I mentioned, we don't want to obstruct the board itself from view of the operator. We want everything to be visible for them, and that's part of the reason why we chose the transparent lid in the first place, electing to use the micro series. So the solar panel is going to be seated inside of the case for the sake of protection, directly above the board itself, such that the displays which are off to the side can still be viewed through the lid. Past designs have used the small square OLED sensor. That's the same one that Isidore described in his sensors and components section. And this works perfectly well for flights or anything that doesn't require a human operator in real time. But the data that this payload is collecting, it's not just for us to analyze back in the lab after the fact. The operator is going to need to view it most likely during the climb and in treacherous conditions. So we need to do everything we can to make the data more accessible during the climb. So we have added 2 LCDs that we'll see not on the board, but next to it. And with the 2 LCDs, we can display 6 lines of text at once, and the text will be considerably larger. And as mentioned, will be viewable through the lid. And with that, I will turn it over to Isidore to talk about flight data.
All right, so this past Sunday, we took the Everest Project, which is this box here, and we sent it up into the stratosphere until it hit about 103,000 feet. We took some data from this flight. This blue line here shows data from the MS5611 pressure sensor, which also took data, or we took temperature data. And then here we have the SHT30 humidity sensor, which, like I mentioned, has that heater in it. So you can see those fluctuations in that temperature quite obviously with that heating cycle. Next, we have humidity data. The humidity or the heater in that humidity sensor is to get rid of that excess condensation that might build up. So when you're looking at this data, you're supposed to collect the bottom points of this. However, this is only really necessary for humidities over 70%. And so we ultimately decided that we're going to get rid of that heater function altogether. And then finally, we have the consumption rate of our battery. And with the solar panel, we were able to maintain about the same current in the system the entire time. So yeah, that is all we have. If anyone has any questions, I think we're out of time, but feel free to come and contact us after.
Thanks.
How are you keeping this? Will this actually be on Everest? And if it is, how will you keep it from getting buried?
One of the ideas that we actually have is just due to its internal heating, it's probably that's going to be just due to the, we don't want to say overloading, but it's going to be generating its own temperature due to the sensors that are going to be inside. So it's possible that due to the change in temperature between both environments, is that we're going to be expecting not much like snow coming up to it, but other different approaches are also being taken into consideration.
In addition, some of these are going to be more portable in nature, so they'll be able to travel with the hikers up the mountain. And then some of them, there are portable or permanent weather stations on Everest. We're going to place them right next to them so we know where they are.
The goal of the project was to have multiple iterations of this case, portability being the key aspect, so that climbers could take them along different routes so we could get a better picture of how climate change is affecting the entire mountain.
Thank you.
How much power do you lose through the glass if it's inside?
Not much. We're still doing tests on solar panel efficiency inside versus outside, but the glass seems to be almost perfectly transparent.
I have two questions. The first one is when you were talking about the GPS, you said that it had a hard time determining the altitude, and I was just wondering if you knew why that was.
Our team, as here at the University of Minnesota Twin Cities, has been having issues with the M08N as a whole. We haven't really pinpointed why it was. We used to have great reception with them, and then all of a sudden we no longer did. But on this last flight, we actually sent up 4 additional GPS units, just trying to get better readings with that data.
Okay, and then my other question was, you talked about how the battery life changed based on the altitude. And I was just wondering why that was. I'm not familiar with batteries and why that might change. Do you know why?
We were not talking about, I don't think we were talking about battery life. We were talking mostly about like the voltage of the solar panel. So what happens is like at different altitudes, you get like much less atmospheric density. So that means that you have less particles interacting and less particles actually absorbing sunlight. So because of that, you get a much greater voltage load output at higher altitudes compared to ground. So because of that, you can like have greater loads at high altitudes.
Thank you.
One last question over here, I think.
Yeah, I don't know if you guys actually already answered this, but you guys were planning on using high altitude balloons to get to that altitude, or what were you using to do these tests?
We're using altitude balloons to test the durability of it, like at more extreme temperatures, or at more extreme altitudes, to see how good it can withstand at those particular heights. However, that would be also interesting to see how it will like last in like long-term scenarios such as with war and Everest.
All right. Thank you.